Good evening, Dr. Munshar.
Good evening, sir. How are you?
Oh, fine, fine, nice, nice connecting with you, sir. We'll start in a few minutes, sir.
Sure.
I'm just checking the. Sir, no, sir.
How are you?
Fine, great, sir.
Long time, huh?
A long time, yeah. I still remember having a coffee in NISM.
Correct.
The conversations we had, very nice.
Absolutely.
Very nice.
It's almost over a decade now.
True, sir. But off and on we have in this social media, thanks to.
Correct.
Very nice. And I'm seeing your progress from various to Jamia Millia Islam, a great.
Yeah.
And, very nice.
Thank you.
Just give me 2 minutes. I will just arrange things.
No issues. Okay.
Josna madam, can you kindly put the welcome slide?
Okay, sir. Okay, sir.
Yeah.
Good evening, sir.
Good evening, madam. In 2 to 3 minutes, we will start, sir. I think we're
Sure. Take your time.
participants are, yeah, slowly. And tomorrow being a Telugu festival, New Year.
You okay? New Year as in
Pardon, sir?
New Year? You said New Year?
New Year, Telugu New Year.
Telugu New Year. Okay.
Yeah, Telugu calendar.
Starts tomorrow. Okay. Happy New Year then.
Thank you so much, sir.
मुझे जरा ऑन कर दे। हाँ माइक ना ना इगो ज्यादा हाँ
Okay. Good evening to all of our esteemed participants this 1 week FDP on Indian financial markets and teaching practice and research perspectives. So we were blessed to have Dr. Munish Shakil sir. Is a passionate and very intense financial markets researcher and very much interested in these issues. We have met several times at Mumbai NISM, National Institute of Securities Markets, a very prestigious SEBI institute. Now it has grown multifold. And this topic is very much dear to the financial researchers. That is essentials of econometrics for research in finance. So I think sometimes I feel Professor Munish Shakil can correct me. All these data science and machine learning is a byproduct of these econometric techniques. Some of them closely follow these econometric methods. Now, for a formal, I request Josna Madam to give a formal welcome to Dr. Munish Shakil sir for kindly accepting our invitation.
Sure, sir. Good evening to one and all who are all presented on this online platform today. And I now welcome Dr. Munish Shakil sir for this FDP day 5 session, sir. And I welcome all the dignitaries and the participants of today's FDP day 4 session. Now, this is the right time to introduce our resource person, Dr. Munish Shakil sir. Sir is having diverse academic and industry experience of over 16 years. And he is certified as a big data analytics professional. Coming to the domain expertise, he is expertised in big data analytics, econometric, time series analysis, co-integration, ECM, conjoint analysis, multi-dimensional scaling, discriminant analysis, logistic regression, artificial neural network, etc. And SAR is having experience of working on software like Hadoop, HiveQL, PigScoop, Flume, HBase, eViews, SPSS, MicroStrategy 9 and R. And sir is presently working with Jamia Millia Islamia. Thank you, sir. Thank you so much. Thank you for being a part of today's FDP day 5 session, sir. Thank you. And once again, I welcome you, sir.
Thank you for such a wonderful.
We have taken the summary from your LinkedIn handles, but sir has a lot more diverse experience for financial market. And previously with the Jindal Global Business School, a very premium institute, and now with the Jamia Millia Islamia University, there's a very prestigious central university. India is known for its research in economics, econometrics, and all these finance areas. Now the floor is yours, Dr. Munish Shakil sir. I request you to yes, sir. Visible. I request you to share the screen, sir.
It is not showing me to, not allowing me to share the screen. The
Let
option
me-
is
I have
inactive.
given that co-host, sir. Can you just mail me, sir? I will share.
All
I will
right.
send the mail.
Okay. Wait for a sec. Your email ID.
Yes, sir. Yeah, I just put it in the chat box, sir.
Let me see. Please check.
Yes, sir. I'm just. Let me. I'm afraid not received it, sir.
One. Not opening.
I could not get it, sir.
You couldn't get it. Hold on.
Maybe some spelling because it is a unique.
No, I have not got any revert. It is
Okay.
correct.
Let me check.
It bounced. Wait, hold on. It bounced back. Okay. Hold on, hold on. Probably I have. Okay. It's GDHAN N
AN two times, sir.
Hmm?
Yeah.
At gmail.com. I repeat, it's GDHAN JHAY
Yes, sir.
@gmail.com. Now please check. Did you get it now?
I'm still.
It has not bounced back.
Yes, sir. Not coming, sir. Is your system not allowing, sir, to share the screen?
No, it's not allowing me.
Okay.
This is inactive actually. Hold on.
Sorry for the interruption. Please bear with us 2 minutes. Manish, can you share to some other mail?
Should I WhatsApp you?
Yeah, that's okay, sir.
Wait. Wait for. Am I audible?
Yes, sir. Yes, sir.
Please check your WhatsApp.
Yeah. I received, sir. I'll
Is
let
it
my
opening?
work. Yes, sir. I will just downloading it, sir. I'm trying to open that. Can you see the screen? Dr. Munish sir, are you able to see the screen?
At my end, I can see. Yes.
Essential econometrics for research and finance.
Yes.
Yeah, all the participants are able to see. Please respond.
Sir,
Just check.
it's visible
Just check.
like WhatsApp screen, sir.
Your WhatsApp is visible to us, sir.
Not this. Okay, okay.
No, PPTs are not visible.
PPTs is not visible here.
Okay, okay. Now, sir.
Yes. Just check all the PPTs you have received, no?
Sir,
Now,
it's okay,
now
sir.
it's visible, sir.
All the slides are visible, right?
Only one slide it is showing, sir, in WhatsApp.
Oh, just check now.
One minute.
There must be 37 odd slides.
Yeah. Yes, I will.
Yeah, it's visible.
Yeah, I will go to that latest slide deck you have sent, sir. Yes. Are you able to see this slide, sir?
Not slide, your WhatsApp, not the slides.
Now, sir?
No, not itself.
Yeah.
Yes, sir.
Are you able to see that?
Yes,
Yeah.
yes.
These 37 slides are there, sir.
Yes, sir.
Yes. All right.
Sorry for the disturbance, sir.
No, this is part and parcel of online thing.
So I request you
All
to
right.
please.
Great. Finally, better late than never.
Yes, sir. Yes, sir.
All right. So, I'm very grateful to you for inviting me as a resource person, and you have given a very warm welcome to me. And we are connecting after almost over a decade, and that's a wonderful feeling. Hopefully, we will meet in person as well. So, without losing much of the time, I'll start with what you said. All the data science and machine learning, yes, is an extension of econometrics. So generally, if you see that it is the economists or the students of economics which are doing well, or they have moved from the economics, statistics, econometrics background to data science and machine learning. So it's a natural progression for the students of economics to move from econometrics to the techniques of predictive analytics and data science and machine learning. Yes, what I would suggest to the participants, and that you have to use a mix of econometrics and machine learning or data science techniques together, because one of the features that will not be covering in this particular session is feature engineering, the time series feature engineering or feature selection, right? So that is very, very important that you now start adopting and using machine learning techniques. And yes, there would be some constraints when it comes to, analyzing such a huge data, because our laptops or systems that we use normally would not support uh, such a huge data set. So you have to use a better system if you can afford that, or you can switch to there is a free resource by Google Colab. So this is a free IDE where you can use the GPU power of on the cloud provided by Google for limited data sets. Secondly, before we formally start, that if you're using SPSS, EViews, or anything else, this is the right time to switch either to R or Python. Very, very important for the students and who would like to use machine learning techniques in their financial research, right? So this is a very important topic that has been provided to me to give my presentation on. And yes, econometrics, and especially the time series econometrics, is very, very essential to understand, to know when it comes to financial market research, because generally what you have most of the times is the time series, financial time series, right? And these financial time series have very peculiar, typical characteristics, or what we call as stylized facts, right? Which can only be possible to capture using the time series econometrics. So very important. So in this particular session, I'll try to cover most of the things, but this is a very, very vast area. So I'll keep the things very basic not too technical. My aim would be to make you understand what financial time series analysis is all about, and how you can use that into your research. So we'll start with the univariate time series modeling, wherein we have just a single variable. So in our time series analysis, what we have is this, that we are interested to know whether the past or current values of the variable of interest has any bearing on the current value of the variable. For example, the past returns are impacting the current returns or not, or sometimes also the value of the shock or the news, or what we call as an error term, has any bearing on the current value of the return or not. So there is a class of models by the name of ARIMA. So this is an acronym for autoregressive integrated moving average models, which we will try to understand what are these and why they are important. From this, we will move to multivariate analysis, then to possibly, if time permits, we'll cover volatility as well. So the slide that you see, some of the concepts are very, very important that you need to understand. So this slide shows the stationarity. So whenever you get our financial time series data, the first thing that you need to check is the stationarity, right? And at the outset, what you need to do is just take the log, right, of your prices and take the log returns. So very important. So why this is important to take the log at the outset is because that it makes the series, or helps the series, become normally distributed, more or less. So if it is not, then there are different methods of even because sometimes what happens that there are certain negative values in the data, and for the negative values you can't take a log. But there is a method wherein you can take the log of a negative value, but that is beyond the scope of this. But I'm just, for the sake of your information, I'm telling this. So what is stationarity? So first up, the moment you get the data, take the log of the data, and then make a graph of that. And you will understand from seeing the graph that the series is not constant. So it is varying from time to time, right? So it is not stationary. It could be possible that the mean and variance are changing over the period of time, right? So you need to check for the stationarity, and if the data is not a stationary, you have to convert that into a stationary data. So the definition that you are seeing on the screen of stationarity, some of the equations that are displayed over here, I'm talking about weak stationarity. I'm not talking about strict stationarity over here. So stationarity per se means that the mean, as you see in your slide, the first equation is a constant. Similarly, the second point is the variance. Of course, it has to be less than infinity, and it is also a constant. So it is not time varying, right? And the third equation is the autocovariance. So this is not autocorrelation that we are interested in, but this is autocovariance. So this is slightly different from autocorrelations, but as a layman, we can understand that both these things actually mean the same. But autocovariance is basically in the units of the variable given, right? So it is sort of not standardized, right? So we need to convert this autocovariance into a autocorrelation function, right? Which is more understandable and more standardized in the sense that the values take the of the autocorrelation values take from -1 to +1, and we understand what is the values of -1 and +1 is stand for. So autocovariance is like it takes the relationship between two different time periods. They may not be adjacent, right? So as I said, because it takes the units of the variable, so it is not very a good measure of autocorrelation. So this tau s, that the last equation that shows the ratio of the two gammas, 0 and gamma s and over gamma 0, it tells you the autocorrelation. It takes the value from -1 to +1. So this way you can tell or find out the autocorrelation function, which you can use a correlogram to display that we will see what kind of functions are shown or not. Now coming to white noise process, this is important again. So generally we talk this concept in the context of the error term. So we want that the error term should be white noise in the sense that its mean is 0 and standard deviation is constant or 1, which is also a constant, right? So what you see over here is again that the mean of the series that you have is mu, which is constant, and the variance is again a constant, which is sigma square. So one thing is important, that this gamma again, which is measure of autocorrelation, takes the value sigma square, a constant variance, if t and r are equal, right? The two time periods, right? Otherwise, it takes the value 0. Now, of course, this is, as I said, is approximately normally distributed. The autocorrelation function with mean 0, and the standard deviation of 1 by tt is the number of observations in your data. Now, two things important over here. One you see is a 5% level of significance statistics or confidence interval that you see on your left, plus minus 1.96 into 1 by root of t. And then you see another equation on the right, which is the Q statistics, or which you call the lung box statistics. So this on the left is for the 1 period autocorrelation. That means autocorrelation between the adjacent periods. When you have on the right the Q statistics, you apply when you want to check that for a number of periods, say from 1 to 5, 1 to 10, all these correlations, or rather autocorrelations, are 0 or not, right? So if you are checking for multiple autocorrelation, in the sense for multiple periods, you apply the Q statistics. If you are only checking for the adjacent autocorrelation between t-1 and t-2, or t-2 and t-3, then you resort using the left equation. So you need to remember this, when to use which kind of test. So for example, I've just explained to you this. So suppose these are the lag values as you see in the diagram, in the table. Yes. Okay. So this is the example that you see, and you have taken the lag up to 5, and each of these lags have a autocorrelation coefficient, which is tau s. In the previous slide, if you see, right, tau s is denoted. So what when I'm saying Q statistics, I'm testing this null hypothesis, h naught tau 1 is equal to 0, tau 2 is equal to 0, tau 3 is equal to, so all of them are simultaneously 0. In that case, so when you're using or checking the autocorrelation for a number of periods, you resort to Q statistics, which is called the lung box test. Please change the slide.
Yes, sir. I'm coming.
Next slide. Next. Yeah, please. All right. So as I said, we will be dealing with ARIMA modeling. So we'll start with a very simple model first. Of course, these are all univariate time series models. The first one is the moving average process. Most of you might be understanding what is this. So this is your current return, suppose, or YT in this case, is a function of the previous error terms, which are also, this error term is also known by the name disturbance term, shock, innovation, or news. So the part of the equation that is not explained by the equation has some impact on the current period returns, right? So this is what you see is a Q order moving average process, right? Of course, we assume that the error term has an expected value or average value of 0 and a constant variance of sigma, right? And T is the time interval it takes from 1 to whatever period that you are interested in, right? But keeping this in mind, generally what happens when we talk of financial market data, stock prices for that matter, lag, and if you're working on whether intraday or intraday data, lags of more than 5 rarely impact the current returns, right? So you have to be very cautious and conscious about this fact that you shouldn't take too much of, lags that you think that 30-day lag would be affecting today's price or return. Very seldom. It can happen, but it is very seldom. Next is a similar one in appearance is the auto retrocession process, or the acronym AR, right? So in this case, this is slightly different from the moving average in the sense that in this case, the past values of the dependent variable itself are the independent variables, which we want to see whether these previous values of the dependent variable is affecting the current value of the dependent variable or not, right? And of course, UT is the error term or the innovation or shock or news, whatever you say. And this is, of course, normally distributed with mean 0 and constant variance. So you can have up to P orders, as I said. You can take 5 lags, 10 lags, 15 lags, whatever. But then we will see later that we need to identify correctly the number of lags that are important. Here, I would like to explain you one thing. Mark my word, which I'm going to use is the word parsimonious. This is very, very important because when somebody who's a beginner researcher, they feel that making the model more complex give value to their model. No, this is not always the case, right? So you have to explain, you have to keep your model complexity low, right? And with minimum number of variables, you need to capture the maximum variance or variation in your data. To set an analogy, you must be aware and know this very known scientist by the name of the late Stephen Hawking, right? What he said that when a new constellation is born in the universe, so it has certain attributes. It has the color, density, size, right? And there are more than 10,000 variables that determine what these parameters, the density, the size, the color, and the shape of the constellation. More than 10,000 variables. So 10,000 variables value will have to change to determine these 4 characteristics of the constellation. But having said this, he said that of these, only 8 variables are good enough that one can predict the shape, size, density, and the shape of the constellation. Look, so 9,992 variables are redundant. Only 8 variables are sufficient enough to accurately or quite precisely, if not 100% accurately, but quite precisely predict the shape, size, color, and the density of the constellation, right? So parsimony or parsimonious model is the one that you should look for. Very, very important. Don't think that if your model has too many variable lags and it is becoming very complex, that means that your model is very, very good. No, that is not the case always. So if you remember, we had calculated the autocorrelation statistics tau s, and which you can represent by a diagram known as correlogram or autocorrelation function graph. Please change the slide. So a related concept to ACF is PACF, right? Which is rather more important. Also known as partial autocorrelation function. So what does it say? It says the partial autocorrelation function, or PACF, denoted by, so it gives you the lag between two periods. Measures the correlation between an observation k periods ago and the current observation. So as an example, it says, so yt minus 1 and say yt minus 3, holding yt minus 2 as constant. So it is kind of seeing the correlation between two periods apart by holding the intermediate periods as constant. So it says between an observation k periods ago and the current observation after controlling for observations at intermediate lags as constant, right? So for example, the PACF for lag 3 would measure the correlation between yt and yt minus 3 after controlling for the effects of yt minus 1 and yt minus 2. So this one is more important to see that it's not just these adjacent lags or periods that we are interested in. There is a possibility that lags which are slightly away from the current period has also some bearing on the current value or not by holding constant the middle values. So generally what you do, you use the ACF and the PACF in conjunction with one another. I will show you the diagrams as well. So with this we come to the ARMA process. So we have done the MA model, the AR model, and this is nothing but the combination of the AR and the MA model. So P stands for the AR, the lag for the AR model. Q stands for the lag of the MA model, and together they forms a ARMA PQ model. So if you see in the diagram, in the equation, is that both the values of the dependent variable itself, right, yt minus 1 to yt minus p, and the corresponding error terms, the MA terms, ut minus 1 to ut minus q, are part of this. We have added together, and simultaneously we are interested in whether these values are kind of impacting the current value of the return or any variable that you, and as usual, ut is the disturbance terms whose we are assuming that its average and variance are constant, and there is no autocorrelation between two disturbance term, ut and us. Again important. All right, this slide, please, next slide. This slide is very, very important in the sense how to interpret the ACF and the PCF things, especially for AR, MA, and ARMA model. Right. So if you are using an autoregressive process or AR model, what you would see in your diagram of ACF is that it is geometrically decaying. Right. As I said, I just explained that the as you move backwards into time, it is very seldom that 10 time periods earlier would have some impact on today's returns. Very, very seldom. So in that sense, it will keep on decaying. On the other hand, a number of non-zero points you will find of PACF, and these points. So what PACF stands for? It stands for, as in the meaning is that definition is that it gives you the correlation between two different time periods by holding some of the intermediate time periods as constant, right? So if you have these at different lags, you find the PACF model, the PACF equation as significant. That will determine the AR model, the lag of the AR model, how many lags you have to take, right? Again, a word of caution in the sense that you have to build. If it suppose it suggests you say 7 lags at different points. So one lag is say YT minus 2, another lag is YT minus 5, then YT minus 7. So in that sense, there are 7 lags which are significant as per the PACF. So you will take 7 lags, but no, statistically, this is what is given and shown, which is true, but you have to have some human touch. So it's not that you just blindly take the 7 lags that is shown to be significant as per the PACF. Rather, you use different permutation and combination of lags and see which of the, and again, the word important is parsimonious, right? And which of the model is more suitable, a model with lesser number of lags or a model with a higher number of lags, right? So very, very important. So parsimony is the keyword for any model building, be it machine learning or econometrics model, or for that matter, any model that you build. Parsimony is the keyword. All right. So for the moving average model, you would see that the number of non-zero points of ACF determines the order of the MA. So how many lags you have to take for an MA model is determined by ACF, unlike the AR model. In that, you have to see the PACF. And for this, a geometrically decaying PACF. So if you find these characteristics, when you are building such a model, you have to see that whether your model is correct or you're building the correct model or not. As for the auto-regressive moving average process, both are geometrically decaying. Very important. I have left the I part, ARIMA part, for the later discussion. So these are the diagram sections you can see. So this is a sample autocorrelation and partial both on the same axis function, an MA model because there is only one lag that we are interested in, and this is how you can see. So it is both are geometrically decreasing with some of the lags as being prominent or significant. So these lags will determine, these bars would determine how many lags that you need to take. Change this slide, please. This is for an MA model of order 2. So both above the axis, above the horizontal axis, above the origin and below the origin, if you see, both are again geometrically decaying in this case. So this is the equation, this is the model or the graph for YT is equal to which you have 2 lags. So this one is for an MA or AR1 model. As I said, the order of this is determined by PACF, and again this is declining. If you see, no, please don't change. If you see the white bar and the black bar stands for ACF, which is though declining. But if you see PACF, it is, except for lag 1, it is all near to 0. Please change. So this is again for AR1 model, more rapidly declining than the previous one. So it depends what characteristics of your data is. So it depends how quickly it decays or not. Next, please. So this is again another model. Depending on the values of AR1 and this, it tells you how quickly or it decays or not. So very few lags are significant, others are not at all significant. Please change. And this slide is very interesting. If you can observe that this is a parallelogram of a series which is non-stationary. So it is not decaying, right? So the effects are persistent, right? So it says sample autocorrelation, partial autocorrelation functions for a non-stationary model, right? So it would look something like this. If you try to build a model on this, right? And if you try to create a ACF function out of this and then plot it, then this is the model, this is the graph that you would see. So the moment you see this graph, that means your series is not stationary. And one of the conditions for a time series analysis that you have to make your data stationary. Very, very important. Please change. This is an ARMA model, both of them. Both have to, as I said, have to be decaying geometrically, which is shown. So you have understood through these graphs that when you try to build a model, be a ARMA model, MA model, or an AR model, what kind of graphs you will get of ACF and PCF, because these are the ones basis on what you determine the order of these models, P, Q, or PQ. P in the case of AR, Q in the case of MA, and PQ in the case of ARMA models. So that will help you determine graphically which model or what number of lags are important. But again, parsimony is the keyword. You have to use different combinations, even if being suggested that 7 lags are, you have to take it statistically, because this is what the statistics show, ACF and PCF show. But still, you please try and check with 3, 4, 5, and whichever is you think is the most appropriate model, you please take that model. Now, 2 things again, very important. When you build a time series, a financial econometrics model, you can have 2 objectives. Keep this in mind, very important thing that I'm going to tell you. One is that either you are just trying to study the relationship between 2 variables, or your objective is of forecasting, right? So these things though rest on the same model, but their objectives are very, very different, right? So when you're trying to establish a relationship between the dependent and the independent variable, you have to build the most accurate of the models. The one which, once you do the diagnostic checking, is the most appropriate one. This is the model that, when taken into consideration, explains the maximum variation in the dependent variable. This is your objective when it comes to relationship. But when it comes to forecasting, it is quite possible the model which shows the best relationship between the dependent and the independent variable might not be good for forecasting. Very important. So this is quite possible that a model which does not perfectly reflect the relationship between the 2 dependent and the independent variables, quite possible is a better model when it comes to forecasting, right? So when you do forecasting, you see the root mean square error, MAE, and all that stuff. So the model which gives you the lowest RMAC is the model that you need to choose for forecasting. But you do not use this RMAC when it comes to establishing a relationship between the dependent and the independent variables. In that case, there are other things that you need to consider. Now, again, a tip for you is that when you do traditional econometrics, and you please don't change, keep it here only. No, that slide only. Next slide. Yeah, please hold on. So what I'm saying, when you do normal regression analysis, CLR, using classical linear regression model, people tend to overweigh the importance of adjusted R square and R square, right? No, but that is not the only statistic that you should be interested in. This is one of the statistics that you should look for, but this is not the only statistics that you need to look for, because sometimes it does happen that a low R square value, but other things are statistics are also relevant, in the sense F test, T test, the number of iterations that the software has taken to converge the model, right? All these things, even your R square is low, but all these things are pretty good, you can still go for the model. But having said this, you should make your R square better if you can. That can only be made if you get larger data, right? So it's not that because in financial time series data or economic time series data, which you will generally find R square to be negative. So in that case, and this is R square, how can that be negative? But this happens. So in that case, you have to look for other statistics which are more relevant. One of the important things, when I said the iterations, whether the software is taking 50 iterations to converge to a model, so basically time taken, 100 iterations, 500 iterations, 1000 iterations. So the larger number of iterations that the computer or the software is taking, that means the software has a difficulty in estimating the parameters of the model. So that model is not good, not stable, right? So if the software is taking less time, less number of iterations, that means it has less difficulty in converging to a value of the parameter. Very important. So moving from univariate to multivariate models, I will discuss only one over here, which is the VAR model, which stands for vector autoregressive model. So this is a very important model when you are trying to study the relationship between two variables, right? And it is quite possible, we will see later, one of the statistics that we will use a model, that both these variables are affecting each other. Both these variables, in the sense, the previous values of these variables are affecting the current values of these variables, right? As you can see in the equations, y1t is not only being affected or impacted by its own previous values, but it is also impacted by the previous values of the y2t variable, right? And similarly, y22 variable is not only impacted by its own previous values, but it is also impacted by the previous values of the y1t variable. So this makes this model known as vector autoregressive model, where again UIT or U1T is the white noise error term. So the simple case that can be entertained is a bivariate VAR model, where there are only two variables, y1t and y2t. You can have y23, y24, y25, and number of things, each of whose current values depend on different combinations of the previous k values of both variables and the error term. So again, parsimony is the keyword. You can have a number of multivariate VAR, right? Where you can have Y1T, Y2T, Y2, Y3T to YKT, as many as you want. So this is trying to establish, and this, mind you, this particular model is better than any univariate model. And this model again is trying to establish the relationship between the two variables in the short run, right? So just 1, 2, 3 periods behind, and it does not display a long-term relationship. This is only a short-term relationship between the variables. So there are certain advantages. I will not talk about the disadvantages of the AR model because every other model has some disadvantages. So why do we actually use VAR model? So the researchers does not need to specify. One of the important thing is that all the variables in this model are considered to be endogenous and not exogenous. So endogenous variables are those that are determined from within the model, right? And exogenous models are the variables which are given from outside. So their values are not determined from within the model, rather their values are given, right? So that is the best part. You don't have to bother about the exogenous variables. All the variables are determined by the model itself. So VRs are more flexible than univariate AR models, as you can see, right? Because of the endogenous variables, and the way they are constructed gives you more room for maneuverability of the model. So provided that there are no this is again very important thing. I will not delve into if you see the model, right, that it only entails the lag values of the independent variables. So the current value of the variable we are not interested in as of now. It can be possible, but we are not interested as of now. So provided that there are no contemporaneous terms on the RHS of the equations, it is possible to simply use OLS separately on each equation. So simple OLS can be used so on both these equations separately. And of course, as I said, the forecasts are better in VARs than this is empirically tested. A related concept to VAR model is grandeur causality, right? So whenever you do VAR model, you have to do this, test the grandeur causality as well. So basically what we are interested. So one thing again important is don't get into thinking that causality, that YT is causing XT or XT is no. This is not the case. It is only just a correlation, right? So YT is causing XT, XT is causing YT is not determined by grandeur causality. It only tells you that both these series are correlated. So correlation computer regression is a static phenomenon, right? It's not dynamic. So it just gives you, it doesn't tell you whether Y is causing X or X is causing Y. It just tells you that there is some kind of a relationship between these two. So is for grandeur causality. So it is an hypothetical test for verifying the usage. The usage of one variable in forecasting another in multivariate time series data with a particular lag, as we have seen in VAR model. Of course, the data needs to be stationary. Otherwise, you can see the ACF and the PACF values, what will happen. So the null hypothesis is that the YT does not grandeur cause XT, right? So that means all the coefficients would be 0. And the alternate hypothesis that grandeur, the YT does grandeur cause XT, that is at least one of the lags of Y is significant, right? So this relationship between the variables could be unidirectional or bidirectional. That means it is possible that yt causes xt, or yt causes xt, or both yt and xt causes each other. So when they both of them are causing each other, then it is bidirectional relationship. So it's if you see the futures and the spot prices, it is quite possible that futures is affecting spot prices and the spot prices affecting the future prices. Although the degree of relationship, the degree of impact could be different. Please change the slide. Next slide. All right. So when we talk about the VAR model, vector autocorrelation model, there are two things again that you need to check. One is the impulse responses, which is the impulse response function, and the variance decomposition. So both of them actually tell you the same thing, but slightly differently. So what does the impulse response function? Trace out the responsiveness of the dependent variables in the VAR to shocks in to each of the variables. So this is what it checks. So whenever you get the output, you need to interpret along these lines. So for each variable from each equation separately, a unit shock is applied to the error, and the effects upon the VR system over time are noted, right? So the shock is given, right, to the error term of both these equations, and then the impact of is observed on the entire system, right? So how the system is behaving. Although the shocks are applied individually to the equations, but the impact is seen on the system of equation as a whole, right? So variance decompositions offer a slightly different method for examining VAR system dynamics. They give the proportion of the movements in the dependent variables that are due to their own shocks versus shocks to the other variables. So as you can see that in the VAR model, the equations, any one equation is also being affected by its own values, previous values, and also being affected by the previous values of the other variable. So this decomposes the variance in the sense that how much is being the current value of the variable is being impacted by its own previous values compared to the values of the other variable, previous values of the other variables. So you need to understand, for example, 70% its own values are affecting itself, and only 30% of the other variables are affecting itself, this current value of the variable. So more or less the same thing, but you need to also find out these values, and these are generally graphs that you need to draw rather than any table or anything else. All right. So moving towards the long run relationship, and yes, please, this slide are also very important. Not just this shortened phenomenon as by the VAR. So when it comes to long run relationship, we are interested in two things. One is the co-integration relationship, and then we go forward and make a error correction model. So there is a kind of a relationship between the co-integration and error correction model. We will just see. But before that, we need to check for the presence of unit root in the model or not. So when you check that your null hypothesis, generally series contains a unit root versus series is stationary. So non-stationarity versus stationarity. Right. So the equation that you see on the left is for the Dickey-Fuller test. And the equation that you, with the delta sign that you see on the right, is for the augmented Dickey-Fuller test. So basically, what we are interested in to test whether phi is 1 or not, or correspondingly this psi on the right hand side equation is 0 or not. Right. So these are the and the model that you see below is what is the augmented decoupleur test. So you have to apply these models, especially generally you apply the ADF model, augmented decoupleur model, to check for the unit root stationarity or not. So before you proceed, in case it is not, then you have to make your series stationary. And the way you can make your series stationary is by, I just tell you one method, which is by differencing. You just have to take the difference of two adjacent values, previous value minus the current value. So once you check for stationarity, if they are non-stationarity, then you make your series stationary by differencing, and then you can proceed to do whatever you want to do. Next slide, please. Next slide. So when I talk of stationarity, when you have the data, right? So suppose you have prices, the closing prices of say stocks of any share or any stock, then you take the log, make a series of that, check the stationarity of that using ADF method. Then you take the return series of the price series, right? Which is also the difference series. Then again apply ADF and check for the stationarity. Generally what happens is that after differencing one, the series becomes stationary. Generally it happens, but sometimes, very rarely though, you have to difference 2 times to make the series stationary. Having said all these things, again a word of caution, because the moment you differentiate, sorry, not differentiate, but you take the difference of the original series, you tend to lose some information, right, which are given in the prices, but because of the differencing, you tend to lose some information that is contained in prices compared to returns. But since we are interested in returns, and the methods are so devised or modeling, that you need to make them stationary. Now coming to this slide of co-integration, as I said, you need to check. So there are these 3 variables, right? A regression model, which are I1, integrated of order 1. So that means after differencing once, yt minus 1, x2t minus x2t minus 1, x3, these series become stationary, right? So if this is the case, then we can say, if the order of integration of these 3 variables is same, then we can say that these variables are co-integrated. All right. So this is what you mean by co-integration, and you have to check, apply co-integration tests, so see whether these variables are co-integrated or not. So change the slide. Okay, yeah, remain here. So again, the residuals, when expressed in this way, can be considered as linear combination of the variables. Typically, this linear combination of variables of I1 variables will itself be I1 of the same order, but it would be obviously be desirable to obtain residuals that are I0, right? So if you remember white noise, so when you do the diagnostic checking, you see whether your error term is white noise or not, right? So it is normally distributed with mean 0 and standard deviation of 1 if you are standardizing, right? Or a constant variance. So typically what happens, we feel good if your series, both the series are of the same order, and a linear combination of that is of the error term of that series was also I1. No, but better is that the error term should be I0. So the answer is that a linear combination of I1 variables will be I0. In other words, stationary if the variables are co-integrated. So this is what is the crux of co-integration. So if 2 variables which we want to check whether they are co-integrated or not, if they are of the same integration or same order of integration, then those variables, when you check the stationarity of their error term, if that comes out to be of order 0, then that means both the variables are co-integrated. This only happens if the variables are co-integrated. This is the point that you need to remember when interpreting the result of co-integration. Next slide. Yeah. Error correction model comes from as a next step for co-integration model. So there is what you see is this delta sign, and we are interested in the beta 2 term, yt minus 1, y gamma xt minus 1. So this is a short-term relation. It not only tells you a long-term relationship between the variables, but this term, beta 2 term, is the one which tells you a short-term adjustment between the two variables. So why error correction or equilibrium model, sometimes also known as equilibrium correction model, in the sense that what happens, it is quite possible that in the long run, the relationship between the variables is such that they, over a period of time, it might become constant. So at whatever lag you see, the relationship is within some range or some bound, right? So if that is breached, right, if one of the variables move out of the equilibrium from the long-term relationship that the variables have, then the model corrects itself, and after some lags, again the variable that has deviated from equilibrium will come back to the equilibrium. So this beta 2 is very, very important in the interpretation of the error correction model. And mind you, if this relationship, if error correction model is valid, then we can say that the variables are co-integrated. Why? Although other way around we can't say. So if the variables are co-integrated, we can have an error correction model. Not always the case, but whenever we have an error correction model, then that means the variables are co-integrated for sure. All right, so we have covered all the models, univariate, VAR, and the long-run relationship. So we move next to the volatility part. Again, volatility is the most studied thing. So I would suggest, as a researcher myself, that studying volatility is important, very, very important in fact. So the option pricing and whatnot is determined by this. But whenever you do research using Garch models or on volatility, make it a bit interesting. What I mean by that just finding the volatility using Garch model of a particular stock or index is, you shouldn't do. I mean, unless it is in some context, maybe context in the sense that you are studying the relationship or volatility pre-COVID, post-COVID, then it makes it interesting. Just because you know Garch modeling and you know that volatility is very important, you should use and do some research. No. Make use of this concept of volatility and Garch model in some special context, that then it will make your research or paper very, very nice. So far what we have been studying is that we were assuming the variance of the series or data to be homoscedastic. that is constant variance, the one which doesn't change from one value to another or over a period of time. The variance remains constant as stationary when we make the data stationary, right? But there are situations wherein it is quite possible that the variance is not constant, that is heteroscedastic, right? So it varies with time. So the Garch model or Garch family of models, including the Arch one, is that the mean in this family of models, the mean of the series is constant over time, but the variance is changing. In that case, we use Garch model. So generally, this is what we observe. But if the mean is changing and the variance constant, then there is some other model. We will not be discussing that here. So as the name suggests, the Arch model, autoregressive, conditionally heteroscedastic. So it captures the heteroscedasticity or variance which is not constant over time. So use a model which does not assume that the variance is constant. Of course, if you find that the variable has heteroscedastic variance, non-constant variance, then you resort to these kind of models. So sigma square is generally, this is the formula, and we assume this to be constant. The mean is assumed to be again constant, right? So if this is time variant, right? If this variance is changing over time, so we need to understand what could be the current value of the variance of the errors plausibly depend upon, right? What is that which is changing this variance? So this leads, so previous squared error terms, this leads to the autoregressive conditional heteroscedastic model for the variance of the errors. So this is known Arch one model because there is only one lag over here, right? Autoregressive, and you just have to check the variance of the errors, whether they are autoregressively conditionally heteroscedastic. So they are dependent on their previous values or not. So, of course, you make a model, right? As you can see in the first bullet point, please, as you can see, change the slide, please. Yes. So these are the steps that you need to have in autoregressive model. This is the full model that you see, where the second equation gives you the Arch model, right? So we are, am I audible, right?
Yes, sir. You are audible, sir.
Okay. So we can easily, so this is the model that you need to check, and so you can extend this model to the general case where you can have any number of lags or q lags of these squared error terms, and you want to check whether these squared error terms has a bearing on this variance or not. So this is an Arch Q model because Q stands for the number of lags. So basically you need to test this. Please change the slide. So this is how you can write. This is just another way of writing the things. So the first form of easier to understand, while the second form is required for simulating from an arch model. So these are two ways of expressing the same thing. So nothing special about the second equation. Please change the slide. All right. So how do you approach this? How do you test the arch effect? Important. So arch effect basically, as you can see in the model, is that it is testing the error term. So error term is what it is. It is noise. It is uh, innovation or shock, right? So that portion of the equation which has remained unexplained, we are taking that and trying to establish that whether the error from the previous equation or previous period is impacting the current period's volatility or not. So this is how you build the model. To go build your model, the arch model, and then you test. Hold on.
Dr. Monisha, that video is not working, I think. Cam.
No, the light has gone at my end.
Oh, okay, fine.
Oh, and the backup has not started yet. So I'm
It's
sorry
okay.
for that.
It's okay.
Luckily, I'm connected with phone also, so
Oh.
I can, yeah.
As a aside, is power cut common in Delhi?
No, it is not.
Okay.
But because it is summers now, some load shedding is there.
Oh,
Because AC starts working everywhere.
okay.
There is some load shedding sometimes.
Okay.
It's rare though. Okay, hold on. So anyhow, so this is how you build the model, obtain the R square values, right? And you then test the arch effect, and arch effect is simple t-test and everything, whether it is 0 or not. Please change. Please change the slide.
Can I go ahead, sir? Next slide.
So this is what we are trying to test. So this is the null hypothesis and the alternate hypothesis. So gamma 1, gamma 2, and gamma 3 all are 0 or they are not. If the value of the test is greater than the critical value from the chi-square distribution, then you reject the null hypothesis. That means there is a presence of a arch effect. Right. So one point that you can do is that sometimes they are directly applied to the returns instead of the error terms. Now, this is the important thing. How do you decide? Next slide. How do we decide on Q? This is the very important thing. And variance, of course. So this becomes, so there is some, since we require this thing, so it's better that we use the Garch model than the arch model. A natural extension of arch model is the Garch model, and any problems that the Garch model or any shortcomings that the arch model has can be rectified or covered by the Garch model. Right. Please change the slide. All right. So So the variance equation is, second bullet point is that what you see is the one that we are interested in. So what you see are the two terms, right? The alpha 1 and the beta, right? So alpha 1 is the coefficient of the arch term and beta is the coefficient of the gauge term. And it is 1 because we are using one lag of the arch term and one lag for the gauge term. So basically it is an ARMA model. Gauge 1 is an ARMA model. So autoregressive because current period volatility sigma t square is dependent on its previous value, and it is also dependent on the error term, right? So hence it is an ARMA model, gauge 1 model. And what we are interested in is how does the sum of alpha 1 plus beta comes out to be, right? Please change the slide. Wait for a sec. So this is how you actually compute the difference, the different variance depending on the lags that you have. And what, as I said, what we are interested in is the sum of the alpha 1 plus beta. Please change the slide. So these are the advantages of gauge model over the arch model. So it is more parsimonious, avoids overfitting, is less likely to breach. Spelling of breach is wrong. So breach non-negativity constraints. Next slide. So this is what, since all the time series analysis is based on the mathematical concept of difference equations, right? Wherein we study the time path of the mathematical model, and we want to see whether by studying the coefficients, when we test of the unit root stationarity or non-stationarity, we are actually checking whether the values of the coefficient is 1 or different from 1. So for the series to be convergent, the value should be less than 1, right? If it is more than 1, then the series will explode, could be divergent. Depending on the values, again, it could be oscillating, it could be non-divergent, explosive. So this is very important that you see in the slide, is that alpha 1 plus beta should be less than 1, which makes the gauge model or the volatility, though persistent, but gradually decays, right? So basically when you use gauge model, basically you're trying to capture a couple of things, right? That whether the volatility in the series of, say, stock returns is pooling itself, is being clustering. Volatility clustering is there. That means that high volatility is followed by high volatility and low volatility is followed by lower volatility. So they are appearing in chunks. Then it also helps to capture leverage effect, as in that the news, whether it is positive or negative in terms of magnitude, will have different effects on the return series. So a negative news of the same magnitude as the positive news will impact the returns more drastically compared to the positive news of the same magnitude. Then leptokurtosis, that means the distribution of the return is such that it has fat tails. So more values are concentrated around the mean, then they are dispersed. So the tails are not extending far off. So as you can see here, alpha 1 plus beta is greater than 1 is termed as non-stationarity invariance. When it is less than 1, it is stationary. And if it is equal to 1, then you have to switch to gauge instead of gauge to I gauge. So this is known as integrated gauge. So for non-stationarity invariance, the conditional variance forecast will not converge to the unconditional value as the horizon increases. This is what I was saying, because the underlying mathematical theory is of difference equation. So it will not converge. That means it is a non-convergent model. Then there is no thing that makes you converge this. So since the model is no longer of the usual linear form, we cannot use OLS. We use another technique by the name of maximum likelihood estimation. The model works by finding the most likely values of the parameters given the actual data. So what happens is that we, in maximum likelihood, that we take the mean, supposedly, hypothetically, we take the mean and the standard deviation, and then try to build a sample around this, the most probable sample from where these mean and variance could have come from. So it will keep on doing this until it converges to some most appropriate or accurate values. Again, same thing. This is the mean equation or the return equation. This is next slide, please. So this is how you estimate. So what you see, this is the mean equation in point number 1, YT, and sigma t square is the mean. Don't have to do this manually. You would be using software. So don't get daunted by the long equations that you see over here. The computer will take care of this. I am done with this. But before I close, 2 things which I've not covered is how to determine. I've covered that using ACF and the PCF, but there is a much better way of determining the lag of a model, that is through Akaike information criterion, AIC, or Schwarz criterion, SC, right? So when I was saying that how to decide on the number of lags in a model is that you have to do some permutation, hit and trial thing, permutation and combination. You have to use different combination of the lags in the model, and then for every time you estimate that model, you will get a AIC value, a Akaike information value. So the model which gives you the lowest value, right, you have to choose that model. That means that number of lags in the model. So that you need to see. So thank you, Dr. Dhananjay, for giving me this opportunity to present these essentials of econometrics for research in finance at your very prestigious institution. And you are doing a wonderful job as an academician. I can see the passion and the energy and the exuberance that you display. I'm in connect with you on the social media, and I take inspiration for what you do. And for the last 10, 12 years, you have taken a huge leap in your career as a professional, and you are doing a wonderful work. And especially the finance lab that you have established, I've seen that. And sometime I would like to physically be present at your institution. I would love to be there if I get a chance.
My pleasure, sir. In fact,
thank you very much, Professor.
Yeah, we had such a wonderful interaction with you, because at NISM, with your vast industry experience and the type of depth you have, sir. I'm really surprised by the participants' enthusiasm, despite the frightening equations. they're there, till the end. The amount of attendance, I'm very much amazed. The flow with which you have explained the equations and the econometrics, the econometric aspect of. In fact, to just add to your presentation, that's how we are we are journeying from a sort of anecdotal finance to an empirical finance, data-oriented finance. How these are all tools to make sense of data, to make sense of big data in finance, huge data. So these models we try to fit them and try to see what type of relations are there in the data and things like that. Whereas we don't want to put our own intuition, our own feelings, or what we call discretionary. We are going from discretionary to more data-driven, empirical.
We have to learn from the data.
Yes, sir. Yeah, where they're learning from the data. Exactly. So that's how that I deliberately have tried to give a sense of what is available. It's a sort of a platter I tried to bring in this FDP. We had some practitioners, we had traders, we had researchers, and we had this concepts of econometrics. So it's a variety of platter of tools we have given. We have tried to provide like technical analysis, various practitioners of in the financial markets, because everybody has his own tool, and you will try to come to financial markets to make money or to make sense of the prices. So somebody has technical tools, fundamental tools, econometric tools, statistical tools, and all these things. So we are very blessed to have you today, sir. Now I request some of the participants to give their observations and some comments or whatever is the benefit of all our audience. And I request at least our Rajesh sir. Rajesh sir is there? He's an expert from Bangalore. He's a very nice person in the area of financial markets. Dr. V. Rajesh sir. Are any other participants would like to comment on this topic?
Just to add, I would like to say to all the participants who are interested in this that you have this econometrics background. I would suggest you move a bit to the next level and use machine learning techniques. Very important, very, very important, because everything is about prediction and forecasting.
Very true.
So, and if you accurately forecast you and minimize errors, then the traders and investors will all be gaining from that. So even now the contemporary techniques are more towards machine learning, which are applied, or artificial intelligence, which are applied to the financial markets, right? And even if you're doing research in that area, so that gets published in good journals.
Very true. Can I request Dr. Mahbub Basha sir to say a few words about this statistical techniques? Dr. Mahbub Basha sir. Any other participant? In the interest of time, I request to provide a.
Yes, sir. Sir, myself, Srinivasara from Guntur, sir.
Please.
Sir. So, first of all, I'm very much thankful, sir, for Narayana College, Engineering College, and its management for organizing a wonderful, FDP program, sir. Actually, in fact, this FDP, as you have rightly said, sir, academicians and practitioners and econometrics, derivatives, etc. It's a wonderful combination of resource persons, sir, actually. Behind this, I feel definitely a lot of hard work from the management and their colleagues, sir. So first, I am thankful and grateful to the all your team, sir. And coming to today's session, sir, it's a wonderful one, sir. Actually, sir, though it is from econometrics, it's more, touching on the financial aspects, in which way these econometrics can be useful in making an effective research in finance. So I'm very thankful to, once again, thankful to Narayana College for bringing this type of resource persons, sir. So I mean, I'm thankful to Dr. Munis Shakil, sir, and all other resource persons. Thank you, one and all, sir, for giving me this wonderful opportunity.
It is only possible because of resource person readily accepting our request, and it's such a beautiful people I'm able to interact with previous when I attended FDPs and various conferences. I was able to get their friendship, so I could request them, and they have readily accepted. Any other participants, sir? I will go to Josna madam to give a formal vote of thanks.
Sir, can I?
Yeah, please, ma'am.
Okay, sir. Sure. Sir, as our Dean, sir, Dr. Dhananjay Garu said that, and some of our participants said that it's a wonderful session. Really, we are all accepting that, and we are all feel very happy to hear you, sir. That is a beautiful session it was. Why? Because there are so many concepts are covered today, and I think these are new concepts to us. What I feel this is new things to me today, and thank you for spending your valuable time for us to share your valuable insights and sharing a valuable information and all those things, sir. On behalf of the Department of Management Studies and all our participants of FDP, we are all thankful to you, sir. Thank you, one and all.
Thanks a lot.
Thank you very much, Dr. Moni Shakil, sir. I plan to catch up with you in Delhi, and also
Sure. Anytime.
I request you to visit one in this part of AP. We are very much happy to host you, sir.
Thanks a lot, sir. I'm obliged. Thanks a lot for giving me this opportunity.
Thank you, sir.
Thank you once again, sir. Thank you.
Okay. Goodbye. Take care.